Hello, this is the first video in a series about the eigenfunctions of the Fourier transform. So I wanted to first discuss some prerequisites for the series so you can follow along. So the first thing is, although in the beginning we will be reviewing some things related to the Fourier transform, it is assumed that you are mildly familiar with some basic Fourier analysis. Also, need to be familiar with linear algebra. And both of these topics would be, some mathematical, with some mathematical maturity. So, upper undergraduate or graduate level. So with that said, we can begin. So the Fourier transform is defined as follows. So we have function f, and we define its Fourier transform at k to be this integral operator. So it's a function of k, and there are x's here. However, the x is a dummy variable. It's the thing being integrated over. The argument k is this right here. So often people write the Fourier transform like this, with the letter c, so x, the Greek letter c here. However, we're just going to be writing with k. It makes it easier. And also, you can write the Fourier transform instead of f hat. You can write a Fourier transform of f at the value k. Now it says xk here. Typically, that's how you would write it if it were integrating over R. X and k were numbers. However, if x and k are vectors, this xk really means dot product. So xk, I'm just abbreviating. I always mean x dot k in general. So if you had a vector, it'd just be a dot product. So xj, kj. Sum from j equals 1 to d. Sometimes you write it as the inner product in this notation. Inner product on rd. So before I continue, I just wanted to mention that there are different conventions for the Fourier transform. In fact, let me share you a Wikipedia page on that. So the Wikipedia page on the Fourier transform has this nice table here in the section table of important Fourier transforms and such, where they mention some of the different conventions. And the important thing about the conventions is that if you pick a different convention, it changes some of the identities, it changes some of the properties of the Fourier transform. So you can't even necessarily say the Fourier transform has this property per se if you're using a different convention. So this is the convention we're using here, except instead of this vector, select this letter C, we're using k. There's a different one where you have 1 over 2 pi here. Its inverse, we typically have 1 over root 2 pi as well. Here's one without a constant 2 pi. There is one where there's a 1 over 2 pi as well. The point is that you can't get rid of the 2 pi in some sense. So here you have 2 pi here, 2 pi here. This has no 2 pi, this has no 2 pi. However, later identities, you will see 2 pi's floating around. So here's 2 pi's here. The point is, to some degree, you can't get rid of the 2 pi's. Something Elias Stein, famous mathematician, says there's the 2 pi, you can't get rid of it. So you have to pick how you want it, and how I learned it from Stein's undergraduate book in Fourier analysis is this one. This is the one I'm going to be using, and it also is the one where the Fourier transform is a unitary operator, which is something that we really want. In fact, there are some properties which we will go over. We'll go over. Don't need to worry about it now. So let's go back to this. It's the Fourier transform. This is just a review of the definition. So when is this thing a well-defined operator? So if we have f that's an L1, that means that this integral here is finite. This is in measure theory sort of thing. So this is Fourier analysis, but in the beginning, I'm going to be assuming some kind of, if you know what L1 and L2 are and stuff like that. So this is basic Hilbert spaces. So this is in real analysis. So it's just, I also am assuming a little real analysis. So if you have an L1 function here, that means that this integral is finite. Then it turns out that its Fourier transform is going to be an L infinity function, which means that it's bounded. and it satisfies this inequality here. That's just this right here. So if you take the Fourier transform, take its absolute value, then by the triangle inequality, you could move the absolute value bars in, and you get absolute value of x, the integral. And that is going to be finite, because if this is true, this is finite. That means that this thing is bounded by this, which is also finite. So if you have an L1 function, its Fourier transform is bound. It also turns out to be a continuous function, and it has some nice other properties. We're not really going to be focusing on those too much. Another fact is that if you have a function that is in L1, so its Fourier transform exists, and it's also in L2, which means that this integral is finite. So it's square integrable. If you assume that f is in L1 and L2, then not only is its Fourier transform in L infinity, that's from up here, because it's in L1, but because it's in L2 as well, its Fourier transform will be in L2. And with the convention of the Fourier transform that we chose is that its Fourier transform will have the same L2 norm as the function. So this identity here, it's the famous identity for the Fourier transform. I believe it's Parseval's identity. So sometimes I write it, I'll just write it over R. If I don't write the R down here, like here, then I'm assuming that it's just the whole domain. So if this is over R, it's over R. If it's not over RD, it's over RD. I'm just abusing notation a little bit, just by suppressing the notation, that's what's called. So let's continue. So we have a function. If it's in L1 and L2, its Fourier transform is in L2. So here we have that the Fourier transform f restricted to the subspace. So L1 intercept L2 is a subspace of L2. It's a subset. Now, what you can do is that if you have any function in L2, you can define its Fourier transform of that function by basically using the fact that this is a dense subspace. So you can pick a sequence of functions here, converging to the function f in L2, general function, and then you define the Fourier transform of this, say that it's going to be converging to this. And the reason why you know that this convergence is going to make sense is from this identity here. And you can check, this is a standard properties. I'm just reviewing it for people, assuming that you've probably seen it before to some degree. And once you have this extension, f is now an operator on L2. It's in some sense abstract, because it's not really written as an integral operator anymore, because this integral doesn't really make sense if f is just a general L2 function. If it's in L1, it does make sense. But if it's in L2, the integral doesn't really make sense. And so it's not really what the Fourier transform is. It's an operator that when you have an L1 function, that's what this is. But if you have a general L2 function, it's just, in some sense, a little bit more abstract, and it satisfies this property here, which is that it doesn't change the norm of a vector. So I have f here, it has a certain length in L2 as a vector in L2, and when I apply the Fourier transform to it, it has that same length. So this is what we call a unitary operator. It doesn't change the length of vectors. Now we have the Fourier inversion. Fourier inversion says that if you have a function that's in L1 and its Fourier transform is in L1 as well, which isn't always the case. We'll have an example of that a little later. If you have f in L1 and Fourier transform is in L1, then you can rewrite the original function as some kind of integral operator of the Fourier transform, and it looks like the Fourier transform, except it's a little different. There's no negative sign up here. Now, what you can do is you can actually write this as a Fourier transform if you wanted to, by putting a negative sign here. Now it looks like a normal Fourier transform. However, you can't just put a negative sign there somewhere. So this is over k, this is k, this is k. So you can't change the k here without doing a change of variables. So what we're going to do is we're going to put the negative sign on the x. So we have to put a negative sign here because we wanted to put a negative sign here, so we have to put another negative sign, so it's still. So what this tells me is that f of x, so this right here is a Fourier transform of the Fourier transform, but then it's applied at negative x. So this is the identity, this is the Fourier inversion identity here. We've written in this a little more abstract way. Now this identity here, I'm sorry, let me continue before I say that. So we have this identity here. Let's define the operator NF. Now, NF is going to be the operator that takes f of x and replaces it with this new function, f of negative x. And if you, on R, you have some kind of function or whatever, f of negative x is going to flip positive and negative. If you're on R2, so it's a function on R2, so you have some kind of shape or whatever. Then doing this right here, we'll take opposite points and swap them. So depending on what the dimension is, it's typically either a rotation or some kind of reflection. So this is just kind of symmetry. It takes the function f and it transforms it into a new function. I'm going to call NF. It's not standard notation, but it's just notation I'm using. Now, with the Fourier transform, Fourier inversion says that if f is in L1 and its Fourier transform is in L1, then this identity holds. So what does this identity say if I rewrite it in terms of this operator n? Well, f and f Fourier transform, those are the same thing. I'm just rewriting in different ways. This says f, Fourier transform, and then n. So Fourier transform squared of n is the same thing as not doing anything. So that's just the identity. So n f squared is identity. Now, one thing about this function here is that if I do it twice, I get the identity, because if you put a negative sign here and you put another one, they cancel each other out. So n squared is the identity. So n is the identity. So n is its own inverse. So that's this right here. So this Fourier inversion identity, which is true as long as the I have some kind of mild assumption on f and its Fourier transform, which will hold for a lot of functions. You know, you can cook up a lot of functions. So for instance, Schwarz functions, which we'll talk about a little later. And there's a lot of these different kind of functions, and both of these conditions are true for that function, those types of function. So anyway, we have this identity. So now what I can do is that you can, because n is its own inverse, you can apply n to both sides. These n's will cancel, and you get Fourier transform squared is n. Now this right here is going to be true for all, applied to all functions f, where these assumptions hold. However, because n is a continuous operator on this space here, just like the Fourier transform is, and even like a dense subspace, a very nice one like this right here, where these assumptions are true, this identity holds on this dense subspace. So what we can show is by continuity, this identity is going to be true everywhere for the general operator of the Fourier transform. So this is something I'm going to be using a little bit later, so I thought I'd mention it as part of like the basic review. So now we're kind of going back to more normal Fourier analysis, which is, suppose we have the Gaussian here. What you can show is if you take the Fourier transform of the Gaussian, then it's the same function. So, you know, there's sometimes this confusion with the x and k mixing it up, but they're saying that the Fourier transform of this function is itself. The function is its own Fourier transform. That is actually the part of the subject of this talk, or the series of talks. So if you have a Fourier transform and you apply it to a function, if you get the same function, that's the same thing as saying that it's an eigenvector with eigenvalue 1. So it's just like if you have a matrix times a vector times lambda v. If you have lambda equals 1, then a v is v. So this vector has eigenvalue 1. In this case, we have a function. So instead of calling it an eigenvector, we call it an eigenfunction. So it's an eigenfunction with eigenvalue 1 for the operator, which is the Fourier transform. So anyway, we have this function, which is its own Fourier transform, which is the same thing as saying it's an eigenfunction with eigenvalue 1. Now, this is a fact, which is that if you have this Fourier transform and you're applying it to not f of x, but f of ax, so maybe f of x is kind of Gaussian like this. Maybe that's not how I draw Gaussian like that. Now, f of ax is maybe squished because here a is going to be bigger than 1. So I've kind of shrunk the function horizontally using some kind of transformation. with this transformation exactly. Now, when you do the Fourier transform, this is f going to fa. I don't want to call it fa. We'll just call it f going to its Fourier transform. I don't really have, so we'll call it f of ax. We'll just do it like that, right? So if you look at its Fourier transform, suppose, I don't know, its Fourier transform looks like this. Instead of its Fourier transform getting narrower, it actually does the opposite. It gets wider. So you can imagine instead of shrinking, it actually expands. It's part of the uncertainty principle. It's just different ideas related to the uncertainty principle. However, this right here can be just checked using a change of variables for the Fourier transform. And this is for a bigger than 0. So as an example, suppose we have this Gaussian here, which is similar to this Gaussian, except there is an a here instead of just no a. In order to apply this identity, you need a times x. So you need some kind of scaling for the variable x. So what we need to do is write it as inside the square. So we're going to move it on the inside as a square root. So we have square root of ax squared. Now we can apply this identity, which says that we have 1 over a. So this is the dimension. And here we're just doing x, and we'll just assume that we're on R. So d equals 1. So Rd is a d-dimensional space, and then we're just going to have 1. So here we have 1 over a. This is going to be 1 over root a. And this here, the Fourier transform gets it applied it at the same variable divided by the a. So this is going to be root a, and it's going to get in the denominator. So I'm going to have root a down here. And you see here that this is another Gaussian. Let's actually distribute this squared first. So we get negative pi x squared over a, and then 1 over square root of a. So this is a different Gaussian with some kind of other scaling factor. So I started with a Gaussian, took its Fourier transform, and then I got a different Gaussian. It's related to this picture here. If I had a Gaussian here and I took its Fourier transform, it'd be a different Gaussian. However, unlike this Gaussian here, which is the same factor here, pi, it became pi. If I have a that's not equal to 1, then this a goes down here. I mean, the a always comes down here. But if a is not equal to 1, then this thing won't be the same thing as this thing, which is a different letter, x or k. And so the shape is actually going to change. So these are going to be very different functions. In order to do this in like a nice way, we're going to normalize these functions. So we're going to normalize them so they have L2 norm 1. So their L2 norm is 1. So I already did the work for this. So you can just say fa of x is this Gaussian here, multiplied by 2a to the 1/4. And then you can show that its L2 norm is 1. Now, if you do its Fourier transform here, well, we know that the a here is going to come down here. So we have an a here. We expect that their Fourier transform will have an a down here. However, we don't know exactly the way the constant is going to work out, because you have to kind of check. You have to use this identity here with this constant to make sure it checks out. So what we expect is, this is true, but I mean, just say, based off this identity we did up here, that we expect the Fourier transform of fa be f of 1 over a times some constant. Now, the nice thing about this is that the constant turns out to be 1. There isn't a constant here, really. It's just 1. And you should expect this to be true, maybe with like a sign or plus or minus or something. But this right here is something you can actually predict just from this and from knowing that Fourier transform is unitary. It doesn't change lengths. So we assumed that fa had length 1 because we normalized it so that it had that property. So this function has length 1 and this function has length 1. So because the function and its Fourier transform have the same length, they should have the same length. That doesn't mean that they have the same sign. That doesn't mean there's maybe a plus or minus here or something. However, we see from this identity up here that there is no plus or minus. There's just some kind of positive constant out here. So this right here is kind of surprising in a certain sense that it kind of worked out nicely. However, the Fourier transform is a nice operation, so it turns out to not work out. So let's see an example. So this is the Gaussian that we had earlier, the standard Gaussian. So this is f1, and this function is its own Fourier transform. Now, if we have function f10, so it's going to be kind of a narrower Gaussian like this. If you do its Fourier transform will be wider. It's just a different Gaussian. They both have length 1. Now what you can do is you can, even though neither of these functions are an eigenfunction of the Fourier transform, because if you do one Fourier transform, it gives you the other one. If you do it of one of them, it gives you the other one. And so it kind of swaps them. So what you can do is you can actually take these two and then put them together to make an eigenfunction. So the idea is that you can just add them. So if you do fa plus f of 1 over a, it's Fourier transform. Well, based off the identities that we had earlier, and knowing that the Fourier transform is linear, you can just apply the Fourier transform to them separately. So if you do the Fourier transform of this one, it gives you f of 1 over a. Do the Fourier transform of this one, it gives you fa. Now that is just this thing and this thing swapped, so I could just rewrite them. So this function here, if I do its Fourier transform, I get the same function. So it is its own Fourier transform. So it's eigenvalue 1. So as a picture of that, if I were to take these two functions here, this narrower one here, and then I'm adding a peak function here, the function that I have is this, which is this weird looking function. This is for a equals 10. For a equals 50, you get a flatter function, which is, I don't know, it's approximately some kind of flat value here. Almost, it is still going to 0. And then it peaks up. Very sharp. However, it's still Fourier transform of itself. The point is that there are going to be many different functions that are Fourier transforms of itself. And you can write out all these weird examples. We're going to be, throughout the series, we're going to be exploring how to generate some of these and some of the properties and stuff like that. Another thing that we just said is that this function is an eigenfunction of the Fourier transform, and it has eigenvalue 1 because it is its own Fourier transform. Now, what you can do is, instead of adding them, what you can do is you can subtract them, and you're going to get an eigenvalue -1 for that. So here we have that here. So if you do the Fourier transform of this one, you get f1 over a. Here you get fa. And then in order to write it like this, you need to make sure that this is the same function. This is not the same function. So you do is you factor out the -1. And now you have fa, need a minus sign here, f, because I factored it out, fa minus f1 over a with the negative sign, and that's the same function here. So this has eigenvalue lambda is -1. So here's a picture of that. If I have f3 here, and then I have f1/3, which is then wider. If you subtract them, you get this wiggly-like function. As another example, suppose you have f of x is the Dirac delta function. Well, what is the Dirac delta function? It's not really a function. It's, I see here I've written it as a tempered distribution. It's a distribution. We're not really going to be talking about that in the series. I just wanted to mention it briefly because you could have Fourier transforms of things that are not functions in L1, which is the functions that we started off talking about with the Fourier transform. Maybe not even in L2. You can find functions that are kind of in between L1 and L2 using kind of interpolation methods. However, the Dirac delta is in none of these. It's not even really a function. So I wanted to at least mention that there are notions of eigenfunctions beyond this kind of paradigm, this perspective. However, I do want to say a little bit about it. So, what is the Dirac delta? Well, the Dirac delta has this property that if you integrate it against some function g of x, and g of x is some kind of continuous function, then this right here is a function that's like 0 everywhere, and then it has an infinite mass at 0. So you can think of delta of x as kind of like a measure at 0, or you can think of it as a function that just has infinite mass at 0. However way you want to think about it. But it turns out that whenever you do this integral, you could just get g of 0, because delta has, basically, it has all the mass centered at 0, and so it just picks up the value g of 0, where g is going to be some kind of continuous function. So this is g of 0 here. So what does that got to do with anything? This is kind of like the property that defines the Dirac delta. So if you're going to come with the Fourier transform of the Dirac delta, maybe like with that, you have the function here, you have the integral, and then it's just basically this identity. If you have 0 here, so it's going to be e to the negative 2 pi I 0 times k. Well, that's just 1. So the Fourier transform of the delta is just 1. So we have this Dirac mass. It has infinite mass here. That's going to be the Fourier transform. Its Fourier transform is the constant function 1. Now, if I add these, I get constant function 1 and then Dirac mass, then constant function 1. And this function is going to be an eigenvector of the Fourier transform with eigenvalue 1. The only thing about it is that it's not going to be in terms of any kind of normal way of thinking about the Fourier transform. It's going to be as a tempered distribution, which is kind of a more abstract notion of what the Fourier transform is, and we're not really going to get into that too much. I just want to say there are different ideas. In fact, you might even look at this picture here and mildly compare it to this picture, where it kind of looks a little flat, and then there's this peak in the middle. However, they're not exactly the same thing. And in fact, there are important differences. One of the important differences is that this peak right here is caused by f50. And f50 is a function has square integral equal to 1. Now, because the function is very large at 0, you can show that this thing right here is going to be definitely less than 1. In fact, it should be getting smaller and smaller because its square is very large in integral. That's where it's contributing. So its absolute value, instead of the absolute value squared, is not going to be quite as big. In fact, this should probably be pretty small. Anyway, so this right here is not 1 when a is going to infinity. It's going to be small. However, the Dirac delta, if you integrate the Dirac delta, well, just using this identity for g equals 1, delta of x times 1, dx is equal to 1. So this has integral 1. So in some sense, it's kind of like an L1 in some sense. And this right here is not really, I mean, I put some question marks here, because this right here is not at all something like this. So you can't identify it with this. You might say its L2 norm is infinite. The point is that this example right here, even though it kind of looks similar, it's kind of like a different idea. The idea here is that you have an L2 function that is then sharply peaked at the origin with integral with L2 norm 1. But this Dirac delta peaked at the origin has L1 1, but L2 is kind of not really a well-defined notion. So so I wanted to give this example and say it's kind of different than the other examples we have. Another example is that you have f is this step function here. So if you had it from -1 to 1, then f would be the characteristic function here, height 1, and then 0 everywhere else. Closed interval here, open here. So this is what this graph is. So what is its Fourier transform? Well, the Fourier transform is going to be the integral of the exponential against this function. Well, the function is only non-zero from -1 to 1. And on this interval, it is identically 1. So it's the same thing as just integrating this exponential from -1 to 1. Now, the exponential, if you use this formula, this has a real part and an imaginary part. And this is also an even function, and this is an odd function. So if I'm integrating an even function over -1 to 1, then that will be what it is. The odd function part will be 0. So if you integrate -1 to 1 of a cosine of 2 pi xk, the I here makes it to a cosine. If you do this integral here, well, what is this integral? Well, it turns out to be sine of 2 pi k. Now you have to divide by 2, and then you evaluate at these two endpoints, so the 2 goes away. So this is what the Fourier transform of this step function is. It's this sinc function. They call it a sinc. Sometimes they write it sinc 2 pi k, and then there's not 2 down here, so you have to put a 2 up here. Anyway, so what does the graph of this function look like? Well, sine of x over x, basically. So you see some kind of function that looks like that. So its Fourier transform is kind of like this nice wiggly function, and this is a step function. Now, if you take the function here, the step, and you add its Fourier transform to it, you get the sinc function here, shifted up by 1, but only on -1 to 1, only on -1 to 1, and outside it's the rest of it's the normal sinc function. But what you get is a sinc function that's kind of has this weird gap in the middle, is broken, it's discontinuous, and it kind of looks a little weird. So this is a one eigenfunction of the Fourier transform. Now you have to be a little careful about what you mean by an eigenfunction, because this function here is not in L1. So it's not in L1, but it is in L2. The reason why it's not in L1 is because you're basically integrating 1 over k dk from, I mean, ignore 0 because the sine of x over x is a nice function at 0. If you just do this from 1 to infinity, this is infinite. But if you were to do it 1 over k squared from 1 to infinity dk, that's going to be finite. So as far as L1 is concerned, I mean, you can go through the details. This function is not in L1. This function is not in L1. I mean, this function is in L1, but its Fourier transform is not in L1. But I mean, this function is in L2, so therefore its Fourier transform is in L2. So these are all well-defined notions as far as L2 is concerned. They also are well-defined as tempered distributions, which are like this Dirac delta example. Notions of functions that are more general and then allow you to take Fourier transforms. And you kind of, tempered distributions are nice because you don't really need to worry too much about some of the stuff that you want to do with Fourier transforms, that if you were to do them with an L1 or L2 function, you could just totally break them and they won't be in L1 or L2 anymore. This example of taking a function and take its Fourier transform, you would like its Fourier transform to be in L1, however, it just isn't. Okay, so that was the example we had. We haven't had any examples for different eigenvalues besides 1 or -1. Here's an example with eigenvalue -I. This is the Gaussian here, and it's multiplied by x. Take its Fourier transform. It's the same function. I mean, I'm kind of abusing notations. Sometimes people usually write k, and then they write k in here. However, I'm just being a little lazy. And it says eigenvalue -I. So f is -IF. And we'll see this example a little later. One thing to note is that this function is odd. So odd means f of -x is -f of x. Because this part is the even part, the part that doesn't care about negative sign. And then this x does care about x. It'll pull the negative sign out. However, all the examples we had so far were even. This is an even function. Its Fourier transform turns out to be even. It's an odd function divided by an odd function. Dirac delta is an even function. You see it's delta and then 0 everywhere else. Its Fourier transform constant is even. It doesn't matter what side you're on. This Gaussian, you can see all these functions are even. They have a symmetry between x and -x. But this is one example, doesn't. It has negative symmetry like this, and it has different eigenvalue. So we'll be exploring that a little bit later. So this is the end of the first video for the series. It's just to introduce kind of the idea. Also, you can get some practice fooling around with kind of some of the problems, some of the functions you've seen with Fourier transforms and you can make your own functions that are Fourier transforms themselves by kind of doing these nice little tricks. In the rest of the series, we'll be exploring some of the structure for where this kind of comes from, and some other things you can say that are in some sense more abstract, but also in some sense more in depth, so you can learn more about the symmetry, but also more about the functional analysis of the Fourier transform as a bounded operator on this Hilbert space L2. So it's the end of the first video, and it was nice talking to you. Looking forward to I hope you like the rest of the series.